All right, what's going on, everybody? Just wanted to let y'all know that it's cool. I just saw this. We got 26 subscribers as of today, so I'm guessing a lot of them came recently because of finals week. Just came to me, but that's pretty cool. You can see here the stats. I really wasn't aiming for this, but kind of happened. But I hope I've been of some help to you guys. So let me know. I mean, either way. But let's go ahead and get started with problem 2.2 for FEA. It reads, for the spring assemblage shown, determine the displacement at node 2 and the forces in each spring element. In other words, local element forces. So we also got to determine the force at F3. They give us displacements for node 3, which is 1 inch in the positive x direction because of the force F3. And they give us the stiffness for K1 and K2 at 1,000 pounds per inch. So let's go ahead and get started. All right, so first thing, right, let's start with the knowns. So this problem is going to be easier because they give us numbers. K1 and K2, that is 1,000. So let me write 1,000 pound per inch. K2 is equal to 1,000 pound per inch. And delta. So once you pull with that force, it's going to move 1 inch, right? Delta is equal to 1 inch. So delta is equal to 1 inch. Now, again, the overall goal is to get this equation. The force vector is equal to the stiffness matrix times the displacement vector. And in basic physics, the force in a spring is force is equal to kx. Now, they put negative kx, but that's just to determine direction, but it's pretty much just force equals kx. And FEA is just a complicated version of it. So, like always, right, they're looking, okay, so we got to get the force, force 3, right, we got to find that force, the forces in each spring element, so those are local element forces. Usually do that last, so you're going to have to find F3 first, and then displacements, but to do all this, you still need your global stiffness matrix, which is a huge K, so we got to go ahead and get started with that one. Step 2. Let's get the little matrices for each spring. So K1, right? And I didn't do a good job of explaining this the first video, so maybe this one's going to help you. So look, check this out. The first spring is between nodes 1 and 2, right? So 1, 2, 1, 2. Again, RC, right? RC cola. Row column, that's how you read this stuff. So this number, what this value is going to be in position row 1 column 1, so it's K11. This one's going to be row 1 column 2. This one is row 2 column 1, and then finally row 2 column 2. And then that number is going to be, right, same thing. So and then I'm not going to go into why this is positive, this one's positive, negative, negative. I guess all you need to know is that that's the way to do it. Just read the book, pretty much. So first spring, it's 1,000 pounds per inch. So it's 1,000 here, negative 1,000, negative 1,000, and 1,000. So that's the first one. K2, right? This one is between nodes 2 and 3. So it's going to be 2, 3, and 2, 3, right? This is going to be row 2 column 2, row 2 column 3, row 3 column 2, and finally row 3 column 3, because it's between 2 and 3. So that's why 2 and 3, 2 and 3. And same thing, they have the same stiffness value, whatever you call that. It's 1,000, negative 1,000, negative 1,000, 1,000. So that's pretty much it. So, and again, you're going to have in this case, you're going to have a 3 by 3. Why? Because there's 3 nodes. 1, 2, 3. It's not the number of springs. It's the number of nodes. So this is going to be your global stiffness matrix is going to be a 3 by 3. Let's go ahead and do this. 1, 2, 3. Let's give ourselves enough space. Let's do 1, 2, 3. I don't know how big it really is gonna be, but just give yourself some room. So at position 1, 1, K11, that's 1,000. So we're gonna put 1,000 here. At position, so check this out. This little matrix between 1 and 2, the nodes here, 1 and 2, 1 and 2. So these four are these four are gonna be these from here to here. So I hope you see that. After a while, if your professor doesn't trick you with moving the nodes around, if you put them in order 1, 2, 3, and not like 2, 1, 3 or something, then that's an easy shortcut. Look, so it's gonna be, you see that little matrix is gonna be here. Now this one is gonna be from this one, this one, this one, this one. So everything's gonna be the same except the 1,000 gets added to this 1,000, which is this one. So this is gonna be 2,000. Hope that makes sense. So it's 1,000 plus 1,000, and then you just continue it. Negative 1,000, negative 1,000. And when I say shortcut, I really mean it, because these things could be up to like a 6 by 6. And on the exam, expect like a 5 by 5 at least. That's what we got. So, and then where you don't have anything, those are just zeros. That's pretty much the answer for the global stiffness matrix. It wasn't asking for it, but you know what? You still need it. So finally, you assemble this equation. So it's gonna be, there's a force 1x, force 2x, force 3x, okay? And that is equal to the global stiffness matrix that we just got. So it's 1,000, negative 1,000, 0. It is negative 1,000, 2,000, negative 1,000, and let's do negative 1,000, so we know 0, 1,000, just so I know where the very center is. There we go. Make it look nice. Then we got U1, U2, and U3. Cool. So now the next step, I didn't mention it in the other video, but when you do FEA, even on the program, not just in problems, they're called boundary conditions. So when I start putting in zeros here or values, those are boundary conditions. So I'll start saying that moving forward. So we start doing the boundary conditions. Node 1 will never move. No matter how much force you put here, it's fixed. So that means this boundary condition is 0. It's never gonna move, right? U2 is gonna move, right? When you pull this is gonna move some distance this way. U3 is going to move. They give us the delta, 1 inch. So U3 will move forward 1 inch after you apply a force. And finally, there is no force 2, right? So if you see here, nothing's acting at that node. It's usually like an arrow with a force value. In this case, it's 0. So force 2 is 0. Force 3, we have one, right? That's the what they're looking to pull with, and there will be a force 1. So here's another trick to these problems. What I've noticed, if I remember correctly too, okay? So don't take my word for it, but usually if you know 2 of these, you don't know the other 2. Does that make sense? So in this case, we don't know U2, but we got the 0 here. We know 0 and 1, but we don't know the 2 here. I hope that makes sense, but I think that's what I remember when I took this class. That was like a dead giveaway. That means what I'm trying to say is if you did the boundary conditions correctly, you should have 1 unknown on each side. So in this case, the unknown would be F1x, F3x, and U2. But notice they're not the same point. That's something I've noticed, but don't take my word for it. But you might be on the right track if you see that. So let's go ahead and assemble the unknown equations. So F1x, right, let's start with the first one. Step 4 is 1,000 times 0, so it's the first row. 1,000 times 0 minus 1,000 U2. Okay, plus 0 times 1, which is 0. So now F2x, now we do the second row. It's negative 1,000 times 0. Oh, F2x is 0. So 0 is equal to negative 1,000 times 0 plus 2,000 U2 minus 1,000, right? 1,000 times 1. F2x, F3x, I'm sorry. F3x is equal to 0 times 0 minus 1,000 U2 plus 1,000. So cool, we got 3 equations, 3 unknowns. That means we could solve this. So look, check it out. I'm looking at equation 2, and we could solve for U2. Just move 1,000 this way, divide by 2,000. Let's go ahead and do that. Perfect. Let me put step 5, equation 2. So I'm gonna move 1,000 this way. So it's 1,000 equals 2,000 U2. And again, hold on. Before I even keep going forward, I'm sorry. You got to make sure everything is in the correct units. So this stiffness matrix is in pounds per inch. This displacement vector is in inches, right? Sometimes they try to trick you. They'll be like, oh, this delta moved 1 inch, but the K2 is 1,000 feet per inch. So remember to convert before you start doing all this. I'll write a comment just in case you miss it, but just keep a lookout on that. So that means, continuing, right, U2 is equal to 0.5 inches. Cool, so we got U2. And again, the goal is to find all U's. In this case, we already know 2. And then finally the third one, and all forces. In this case, we already know 1 of them. But that's the main goal. Just make sure you know every single force, every single displacement, and you're on the right track. So let's go ahead, step 6. Now that we have U2, we can find force 1. So equation 1, plug in U2, F1x is equal to negative 1,000 times 0.5. I'm not writing units because I already know everything's in pounds and inches. So force 1 will be 500, negative 500. Okay, so you'll see what I'm about to do right now. Negative 500. Now, yeah, a force really can't be negative, but that just means it's going, we assumed this is the positive direction, right? In these problems, whatever number you're getting, it's always in the positive x direction. So this is what that means. Negative 500 pounds going that way. That just means F1x is equal to 500 pounds going this way. Okay, so either answer is correct, but if you want to make sure you don't get points deducted, always put in this arrow. And if he marks you wrong, go to his office hours or tell him, hey, I put negative 500, but I put this direction, so technically I'm right. Okay, so just, that's a good trick. Okay, so step 7, let's see, what could we do now? Oh, look, we also have U2, so we could just find F3x. So equation 3. And this is equation 1, 2, and 3, okay, just FYI. Equation 3, F3x is equal to negative 1,000 times 0.5, right, U2, plus 1,000. That means F3x is equal to, that's negative 500 plus 1,000, that's 500 pounds. And that is, again, going that way. So any number you get, it's always this way because that's our orientation right here, right? So cool. And that kind of makes sense, right? Think about it. So that's what I love about structural engineering, FEA. You can kind of see it make sense. So if you're pulling with 500 going this way, that means this one is pushing this way 500. Because nothing's happening at force 2, so you can't say that the force is split up between these two nodes, because we already know nothing's going on at node 2. So that means if you're pulling this way 500, you got to pull this way 500, right? Newton's law or some shit like that. I forgot. 500. So you're pretty much done with the problem, but remember, you got to find the local element forces. And that just means, you'll see what it means, but let me just show you first. So local element. forces. Cool. So we're gonna do the first spring. So local element forces are for each spring. So check this out. Let me go ahead and do this. F1x, F2x. And just FYI, these problems get crazy. So you'll have like F1x, F2x, F1y, F2y, moment 1y, moment 1x, and it's just crazy as hell. Just, you'll see later on. So F1x, F2x is equal to the matrix of that spring. We're doing the first spring. So this little matrix, which is 1,000, negative 1,000, negative 1,000, 1,000. And the displacement vector. In this case, we already know it's just the first two, U1 and U2, right? Because nodes 1, nodes 2. So that is 0.5 for U2 and 0 for the first one, right? 0, 0.5. Cool. So it's pretty much the same steps, right? F1x, let me move it up in case you can't see. F1x is equal to 1,000 times 0 minus 1,000 times 0.5. Let me go ahead and write it down. So you go 1,000 times 0.5. Okay. And F2x is equal to negative 1,000 times 0 plus 1,000 times 0.5. So that means F1x is equal to negative 500 pounds. And F2x is equal to 500 pounds. Again, the arrows. So both that way. Okay. So I'm gonna go ahead and box this. That's the answer. And I'll explain it in a bit. We're not done yet. So that's the first element. Now we gotta do the second one, second spring. So that's gonna be, let me move it up again. F2x, right? Because it's between nodes 2 and 3. So F2x, F3x equals the stiffness matrix for number 2. And in this case, they're the same, but that will not always be the case, just FYI. So 1,000, negative 1,000, negative 1,000, 1,000, right? Times the displacement vector. In this case, it's U2, U3. So it's 0.51. 0.51. Because again, it's between nodes 2 and 3. So it's kind of just, the numbers keep getting shifted down 1, if that makes sense. Here's 0, 0.5, now it's 0.51. If we had another node, it would have been 1 up top and whatever the displacement would be. But let's go ahead and continue. F2x equals 1,000, right? This 1,000 times 0.5 minus 1,000 times 1. So again, it's 1,000 times 0.5 minus 1,000 times 1. F3x is equal to negative 1,000 times 0.5 plus 1,000 times 1. All right, so this is 500 minus 1,000. That means F2x is equal to negative 500 pounds going this way. And then F3x is equal to 500. Because this is negative 500, that's 1,000. So 500 pounds going this way. All right, so that's the answer right there. So let me explain what this means. With the paper, cool. All right, so the element forces at right here. If you were to just look at this little thing, like forget about the whole big picture, just focus on this element right here. On both, there's something obviously going on at both sides because of this force, but we're just focused on this little thing right here, right there, right? So in this little volume, or whatever you would call it, 500 is pulling the negative 500, but since it's negative, it's coming this way, right? So there's this force pulling 500, and then there's another force here pulling 500. That's F2. So it's pretty much an equilibrium just in this little volume of space. Now for the next one, from here to here, that same 500 that is pushing this way, this one right here, remember? It's actually doing it this way now, counteracting it. And because this one's pulling it this way. So if you look at this, these actually cancel out if you add them together. 500 pounds going this way, and then 500 pounds going this way, right? Because if you get rid of the negative, that arrow changes, so it comes this to the left. So they cancel out, which is what you want, right? Because right here, our F2x was 0. So in terms of local element forces, there is a force at 2, but it's equal and opposite, which is why this is 0. And then finally, this is only because we have 3 nodes, but F3 should equal the big F3, so 500 pounds going this way. And then the big F1 should equal the little F1. Now, if you add more nodes, it gets crazier, right? But in this case, F3 should equal this F3. Because after that, we're done. We don't have a F4. We don't have another node. But that's pretty much it for this video. Again, you got to know how to do the little element matrices, how to find the position for each one. This is between nodes 1 and 2. So this matrix is going to have this position on the big matrix. And that's pretty much it. They get easier as you go along, but just one step at a time. And there you go.